All right, hi guys. So we're going to be doing 5.4. This is basically just expanding on the integral, a couple of uses here and there. So let's just jump straight into it. Yeah, so I don't think I've said it specifically in my previous videos. I'm sure by now I've said it in class. I'm recording these videos kind of ahead. But you really need to know your antiderivatives, right? Just like you need to know your derivatives, right? So if I ask you what's the derivative of x squared or sine or cosine x or e to the x or ln x, right? All that stuff. You should know those derivatives. And now that we're getting here, you should know those antiderivatives as well. Just, right off the bat, like what's the antiderivative of cosine? Right? It's gonna be sine x, okay? Things like that, right? Awesome. Okay, so let's just get a little bit more used to power rule here. Okay, so let's do some practice. We've done some examples previously, so let me just give you a couple examples here, and you're gonna try them. All right. So in red, I just wrote the rule again for the antiderivative. Now, since we're doing definite integrals, you don't need the plus c, right? But go ahead and pause here and try these examples. Okay. Hopefully it doesn't take too long, and then I'll come back with the answers. So pause the video here. Right, here are the solutions. So 256 over 15 and negative 10 thirds. So let's just walk through it very quickly. You can pause here and check your answers if you want. So I distributed the root t, but I also wrote it as rational exponents. That way we can use the power rule, right? So I did the power rule, got the antiderivative. Make sure you want to add one to the exponent, then reciprocate the exponents, okay? Then I plugged in the upper bound and the lower bound, right? Upper bound minus lower bound. Okay, and then just algebra from there. Okay, algebra from there. Same exact thing for this guy here. Okay, so let's talk about something called the net change theorem. Okay, what is this saying? Well, um, if think about it, just kind of conceptually here, say we're at some starting value, and then we change by some certain amount, and that'll be our final value, right? Okay. So we're going to make use of something here. But kind of the sentence, how it comes in is the new value of a changing quantity, the new value of a changing quantity equals the initial value, plus the um, the net change. So, but this is going to be the integral of the rate, the rate of change. Okay. Okay, so what's going on there? Well, so remember our two pieces, So the integral from a to b of f of x dx, this is capital F of b minus capital F of a. Okay. So that's our evaluation tool, right? We have a function, we find the antiderivative of it, and then we plug in the bound to do that subtraction. Okay, we just did that right here, right? The other thing is the derivative of my antiderivative is my original function. That was a little weird to say out loud, right? But the derivative of capital F is little f, right? That's the whole point. Capital F is the antiderivative of f. Okay. Now, I'm basically just going to plug this in right here for little f, okay? And then move things around. So we put these two things together. We get the integral from a to b of capital F prime of x dx equals capital F of b minus capital F of a, okay? So usually it's most useful to think of it in as that top line. Now, for what we're going to be using, I want this bottom line here, and then I'm actually going to add f of a to both sides, okay? And then flip it around. So f of b equals f of a plus integral a to b f prime of x dx. Okay. Okay. So this is it. My new value equals my old value plus, and this is the amount of change. It's the integral. It's the integral of the rate of change, right? The derivative is the rate of change. Okay. But you could think of just that whole expression as the amount of change that's happening. Okay. Okay. So let's try it. Let's try it. Okay. So let's say we're given v of t equals 3t minus 5 meters per second. Okay. And then we're on the interval t on the interval 0 to 3. Okay. And I want to find the net displacement of the particle. Okay. The net displacement. So displacement, let's just write the sentence here. Find the net displacement. Okay. Displacement is just how far we moved. It doesn't care about where you start or where you end. It cares how far you moved to get from the start to the end. Okay. So it's that distance or whatever. Okay. So like I said, it doesn't matter where we are or where we start or where we end, right? If I travel 5 feet from here to, you know, my bathroom, that displacement is 5 feet. It doesn't matter that it was here to my bathroom. It could be, from my fridge to my pantry or something, right? The displacement is just how far you travel to get from the start to the finish. Okay. Now, um, remember this equation up here. Um, so net displacement, that's going to equal whatever my end position is minus my initial position, right? So just think about it like on a number line, right? If I'm at an x coordinate 6, or I start at 1 and I go to 6, how far did I travel? Well, I traveled 5, units, let's say meters, right? How did you get that though? You have to do your final position minus your initial position, and that gives you how far you traveled, okay? Same thing here, just more generally. It's my final position minus my initial position. But you notice we're talking about velocity and position here. So let's actually use those function letters, right? So we have v of t equals 3t minus 5, and s of t, that's my position. Okay. All right. Well, that means my displacement for our problem is going to equal s of 3 minus s of 0, right? My position at time equals 3 minus my position at time equals 0. Okay. Well, um, using this equation right here, f of b minus f of a, that's just the integral. Okay. So s of 3 minus s of 0 equals the integral 0 to 3 of s prime of t dt, right? So we're just using s instead of capital F, right? Again, the function name doesn't matter, the letter doesn't matter. All the relationships matter, okay? So I've got f's on the outside and then f prime on the inside of the integral. Here it's everything's the same, just with s. And then I've got my bounds in there as well, 0 and 3. Okay. Now, what's s prime? Okay. S prime is my velocity. So this is simply 3t minus 5. So s prime is velocity, v prime is acceleration. All right. Now that we have this, we can do our antiderivative. Okay. Just quickly pause here and try it on your own if you want. So we should get 3 halves t squared minus 5t, and then my bounds. Okay. If you notice, if we plug in 0, we'll get 0. Okay, so we can just simply ignore that. And this is going to be not, excuse me, 27 over 2 minus 15, which is negative 3 over 2. Okay. And this is my um, displacement, the distance I traveled. So that's meters. Okay. So again, I don't know where I am at time equals 0. I don't know where I am at time equals 3, but to get the distance traveled between those two positions, I actually went negative 3 over 2 meters, right? So I went to the left, 3 over 2 meters, 1.5 meters. Okay. Um, okay. So let's do one more example, and then I'll have you guys try something. So we're not going to look at net change. Let's look at, excuse me, displacement. So these are the classic words you'll see. So displacement. So we're not going to look at displacement. We're going to look at total distance traveled. Okay, and if you guys remember, we talked about this at the end of last video. Okay, not displacement, excuse me. Total distance traveled. First couple letters are the same. It tricked me. It's total distance traveled. Okay, but we're going to do the same function. Okay. So if you guys remember, I talked about this last time. With our velocity, we could be, overlapping, going back and forth. So my total distance traveled is accumulating, but my displacement is not, right? Um, okay. So again, I'll just give a similar example, right? So imagine we're a particle on a line, on the number line. So I could be traveling, back and forth like this or whatever. My displacement is simply the distance between my start and finish. My total distance traveled is exactly what it says. It's not just the d distance between the two endpoints. I need to look at every single um, part of this path I traveled on and add up all that distance I traveled. Okay. So if you guys remember how we do that, total distance traveled, there's not really a good what would you call it? Like name for it. So I'll just, total distance traveled TDT. That's the integral of the absolute value of your velocity. Absolute value of your velocity. Okay. Now, if you remember, when we did an example of this earlier, the function was already positive, or already always positive. So the absolute values didn't do anything. Now here, this function is not always positive. Okay. So what we're going to need to do, there's two ways to do this. One way is to graph it. Okay. So let's show that way first. So we're doing the interval 0 to 3. So this is my t-axis. And then my v of t-axis is my function. So it's got a y-intercept of -5. So let's call this -5, -4, -3, -2, -1. Okay. And that's got a slope of 3. So it goes up 3 over 1, 1, 2, 3, 4, 5. Um, 1, 2, 3 over 1. 1, 2, 3 over 1. Okay, so this is my velocity. But notice here, part of it is negative, part of it is positive. Okay, so what we're going to do is split it into two integrals. One integral on this interval where we're negative, and one integral on this interval where we're positive, right? Because on the positive interval, absolute value doesn't change anything. On the negative interval, it changes the sign, right? That's how you could do it for graphing. And the other way to do it is essentially exactly how you'll find this middle point. How do I know where to do my left integral, my right integral? What are the bounds for that, right? How do I find that point there? Well, this is essentially the second way to do it, which is probably what I would recommend because graphing can take a while. What you do is you just set your function equal to 0. Okay. So I have 3t minus 5 equals 0, 3t equals 5, t equals 5/3. Okay. So if you graphed the function, you know now, oh, okay, I can split my integral up from 0 to 5/3 and 5/3 to 3, and then jump to the next step. If you only did this, where you set equal to 0, you don't know which half is positive or negative. Okay. right? Imagining, let's, imagine we didn't do the graph, right? So now I've split it into two intervals, 0 to 5/3, and then 5/3 to 3. And we will do integrals on both those intervals. But which one is my function positive? Which one is my function negative? Okay. So the way to figure it out, you just plug in a point, right? Just plug in a point. So here we can try t equals 2, and here we can try t equals 1. Okay, and you just plug in v of 1, v of 2. Okay, and what you'll find is this is in fact negative, this is in fact positive. Okay, yeah, so set the function velocity equal to 0. That tells you where to cut up your full interval into little pieces. And then on each of those pieces, figure out, is your velocity negative or is it positive? Okay. Now, why do we need to know that? Well, let's just bring it down here so I have enough space. So this is equal to the integral 0 to 5/3, absolute value 3t minus 5 dt, and then the integrals 5/3 to 3, absolute value 3t minus 5. Okay. So remember, um, absolute values on something positive doesn't do anything. So for this integral here, absolute value doesn't do anything. I can just simply get rid of it. For the left integral where we are negative, I have to multiply by a negative to make it positive again. Okay. So look at all this area here is negative. If I multiply all of this by another negative sign, it would all become positive and jump up here. Now it's all positive. Okay. Right? That's what absolute value does. It makes it positive. Now, make it positive isn't a mathematical operation. Okay. But if you have a negative quantity and you multiply it by a -1, that is a mathematical operation to make it positive. Okay. So what we're going to do is I'm sticking negative on this guy because that's my negative quantity. So then two negatives cancel out. And then this guy, I can just simply get rid of the absolute values. And this is what I have. Okay. So notice I have a minus in front of the integral that was a negative area, and then a plus in front of the integral that was positive. So now everything here is a positive. And now we can just do the integrals. So one nice thing about putting the negative on the outside is when we do our antiderivatives, they're both the same function, right? They're both 3t minus 5 on the inside. So my antiderivatives will be the same. Okay, so here it's 3 over 2 t squared minus 5t, right? We did last problem as well. 3 over 2 t squared minus 5t. Okay, the important thing to keep in mind here is these two guys are separate. They're separate. Okay, so we got to be careful with our parentheses. We got to be careful with our parentheses. So let's do it. So normally what we do is we do one group of parentheses minus another group of parentheses and we plug in our bounds there, right? But because we have two of these happening in one line, we're going to put brackets around them as well. Okay. So like this. Okay. So first half for my first bracket, and notice there's a minus sign out front. That's also why we need the big bracket. So I'll plug in 5/3 here. So 3/2, 5/3 squared minus 5/5. Okay, then I'll plug in 0. So 3 over, well, actually, if you plug in 0, you notice that's just a big fat 0. Then I can plug in 3 here. So 3/2, 3 squared minus 5 times 3. And then 5/3 again. 3/2 squared minus 5. And then 5/3 plugged in. Okay, 5/3 plugged in there. Okay. Now we have to be super careful about what's happening. So what I would recommend is deal with all the stuff in the big brackets first, then combine after that. Okay. And that is following PEMDAS. Okay. So let's do this. So I have 3/2 times 25 over 9 minus 25 over 3. Okay, it looks like the 3 and the 9 can cancel. That's 25 over 6 minus 25 over 3. So this is negative 25 over 6. Okay, of course, you could plug that in your calculator, turn it to a fraction. That's what you get. But remember, this is all in the brackets with a minus sign out front. You can do this one here as well. So this is 27 over 2 minus 15 minus and then the same thing we got earlier. So 3 over 2 times 25 over 9 minus 25 over 3, right? Notice this guy here and this guy here are the same, okay? With this, because we cut it up, there's multiple spots where our 5/3 bound appears. Okay, so there'll be duplicates here. So we can just go ahead and finish this. So 27 over 2 minus 15 is negative 3 over 2. And then this is minus the negative 25 over 6. Okay. And again, this is in the big brackets and with the plus. Okay. So we're looking at this line here. Okay. So I have plus 25 over 6, minus 3 halves, plus 25 over 6. So this is 25 over 3 minus 3 halves, which is 41 over 6 meters. Okay. So notice what happened. My displacement is negative 3 over 2 meters, right? 1.5 meters. I moved 1.5 meters to the left. But this 41 over 6 is actually the distance I traveled. And if you calculate it out, it's close to 7 meters. Okay. So even though I only moved 1.5 meters to the left, my entire journey involved traveling 7 meters. Okay. Almost 7. It's not exactly 7. Okay. And that's that. Okay. So leave that on the board. And then I want you guys to go ahead and try this one. For this one, you'll have to remember your antiderivative. So do both. So find displacement and total distance traveled. Okay. And we have velocity equals 1/2 e to the t minus 2. And then, oh, excuse me, let me pause here for just a second. All right, I'm gonna make it a little easier on you guys. Let's not call it that. Let's call it e to the t minus e. Okay, so e to the t is the exponential, e is just the number, 2.7, blah, blah, blah. And let's look at the interval 0 to 2 for t. Okay, just go ahead and pause here. Try and do both. And let me see if I can get everything on the board here. Okay, there's that. And then the net displacement is that guy right there. Okay, let's go ahead and work on it. Okay, so I've got both parts here. Displacement's quicker just because it just requires the integral, right? And no splitting up the bounds. But we just do the integral of the velocity. Okay. Um, and maybe this tricked you up. Let's see, right? So e to the t, antiderivative, that's e to the t. Antiderivative of e is e times t, right? Because e is just a constant. What's the antiderivative of 5? It's 5x or 5t. What's the antiderivative of negative 1,000? It's negative 1,000t or negative 1,000x, right? Whatever variable you're doing. Okay. So then what's the antiderivative of negative e? It's negative e times t. Okay. Hopefully you guys got that. If you didn't, hopefully you understand now. Right? Antiderivative, I mean, we've been doing it. The antiderivative of a constant dx equals that constant times x, right? And then the plus c if you're doing an indefinite integral, right? Okay, but then I plugged in the bounds, so plug in 2 minus plug in 0, and then do all that algebra, and we get about 0.952. Okay, e squared and 2e are different, right? E squared, that's an exponent of 2, and then 2 times e, um, yeah, those are different, right? It'd be like saying, excuse me, it'd be like saying 5 squared and 2 times 5 are the same, right? They're not. Okay. Hopefully nobody was thinking that, but if you were, hopefully it makes sense now. Okay. All right. Total distance travel takes a little bit longer, but same exact process that we did earlier. Okay. So yeah, we have to integrate the absolute value of the function. We set the velocity equal to 0. Okay. So we should get e to the t equals e. Now, you could take natural log on both sides like I do. Okay. Because natural log and e cancel. So we just get t equals 1. You could also notice I have e to the t equals e to the 1. So because those bases are the same, the exponents have to be the same as well. All right, so t equals 1 that way. Okay. Then we split into our two intervals, 0 to 1, 1 to 2, and then figure out is my velocity positive or negative on those intervals. Okay. So you just plug in a value in the middle there, kind of like the first derivative test, right? Exactly like it actually. Okay. So yeah, we split this up. So now we have let me just focus on the first line here. Now we have the two integrals. We split it up 0 to 1, 1 to 2, and then we do the signs. Okay. So because my velocity from 0 to 1 is a negative, I have to multiply by another negative there. Okay. Then the integral 1 to 2 is fine. Okay. Now we do the excuse me. We do the antiderivatives. Okay, same antiderivative as in net displacement. Okay. But then when we split it up, you just want to be careful. So this bracket stays in brackets, and then this guy here stays in brackets as well. And the signs are still there. Okay. So this negative is here, this plus is here. Okay. Okay. Then the rest of it's basically algebra, exponent stuff, seeing things cancel. So e to the 1 and e times 1, those are the same, right? E to the 1 is just e times 1 is just e. So stuff cancels all the way down until the very end where our answer looks like it should be the same, but it's not, right? It's e squared minus 2e plus 1. In the displacement problem, we had a minus 1. Okay, so this is about 2.952. Okay, alrighty. So that's like the net change. Okay, so let's do another example here. Kind of a more real world quote unquote example. Um, so let's say a boat consumes gas at a rate of 5 minus 0.1 T cubed gallons per hour. Okay. How much gas is used in uh, the first 2 hours? Okay. Right. And this is exactly our net change formula. Okay. It's basically analogous to net displacement. Okay. Except we're not doing displacement, we're using gas, but it's the same idea. So net change, that's going to equal the integral and then 0 to 2, because we're talking about the first 2 hours, of my rate. So my rate is the 5 minus zero point 0.1 t cubed. Okay, so then we can do this. So what's the antiderivative of 5? It's 5t. And then minus zero point 0.1 over 4, because we add 1 to the exponent and divide. Okay. So again, 0 becomes 0. So we really just only have to plug in 5. So it's 5. I guess we don't need parentheses either. So I have 5 times 2 minus 0.1 over 4 t to the 4. So this is 10 minus 0.4, which is 9.6 gallons. Okay. Units might be tough to really think about. Um, so think about the question if that helps. How many gas are we using? Or how many, right? How much gas are we using? Well, gas, the units for that is gallons. So we're using 9.6 gallons. Okay. Nothing to do with time or anything, right? How much, if I ask you how much gas are you using, you're not going to say 5 gallons an hour because that'd be your rate. I'm just asking about the total amount. Okay. Um, Wonderful. Yeah. But again, that was pretty much analogous to the displacement idea. Okay. Now we're going to look at integrating even and odd functions. Okay. So hopefully you guys remember what those are from algebra. It's okay if you don't though. So let's recap it here. An even function satisfies this property where the function equals if you plug in negative x to the function. Okay. What that means is your graph is symmetrical across the y-axis. Okay. So whatever happens on the y-axis, maybe, something like this. Okay. It's symmetrical, so it's going to look something like this. Okay, I did my best to mirror it, but hopefully you guys can see what's happening, right? So whatever happens on it's mirrored, right, on the left and the right. Odd is a similar equation representation, but it's actually f of x equals negative f of negative x. Okay. So that's rotationally symmetric. So whatever happens over here, you rotate 180 degrees. Okay, that's close enough. Yeah, so if you imagine rotating 180 degrees, um, it's the same. Okay. Okay. So it just so happens, and maybe you can tell if we're going to be doing the integral, maybe you can tell from the picture. Okay. So let's look at an even function. So if I'm integrating negative a to a of this even function, this is actually just double the integral 0 to a of f of x dx. Okay. So if you notice here, if I pick a spot, I'm integrating negative a to a, right? This integral in this section, notice it's just double if I were to do the integral on the right-hand side, right? If I take that green area and double it, I'll get the entire red area. Similar thing for odd functions, so negative a to a f of x dx, okay? But notice what happens if I, do here to here. So this is a, negative a, and I'm doing this integral now. Think about what happens. That left side has a negative sign attached to it because it's below the x-axis. The right-hand side has a positive sign attached to it because it's above the x-axis. So they have the same areas, but one is negative, one is positive. So we get a big fat zero. Big fat zero. They cancel each other out. They cancel each other out. Okay? They cancel each other out. So let's go ahead and try it. Okay, let's try it. Okay, x. Example, integral negative 2 to 2, 3x to the 8th minus 2 dx. Okay, so remember, we got to check two things. There's two things here. Are the bounds negative a to a, and then is f of x even? Okay, or odd, or odd. Okay. Well, the bounds are definitely negative a to a, right? It's negative 2 to 2. So that's a check. So that's a check. Is my function even or odd? Okay. So with polynomials, we can tell by just looking at the exponents of the powers. But generally, this is how you would tell. What you do is for this, you test by you plug negative x into your function. Okay. So this is going to be 3 times negative x to the 8th minus 2. Okay. So wherever you see x in your function, you're going to replace it with parentheses negative x and then simplify. So negative x to the 8, negative x to the 8th. Well, that's negative x times negative x 8 times, right? So there's an even number of negatives and they cancel each other out. And I get 3x to the 8 minus 2. Notice that's exactly my original. That's exactly my original. So f of negative x equals the original f of x. That's an even function. Okay, so this integral here is double the integral 0 to 2, 3x to the 8 minus 2 dx. Okay, it's an even function over symmetrical bounds, right? Negative 2 to 2. So it's double from 0 to 2. Okay, and now we can just do it. The reason this one is useful is because you got a 0 in there, and usually 0 is helpful in evaluating integrals, right? So I have a 2 out front, and now let's do our antiderivative. So I add 1 to the power, so I have 3 over 9, and then minus 2x. Okay, so then this is 2, plug in my bounds. Well, actually, if I plug in 0, I get 0, right? So I could just ignore that. I have, well, 3 over 9 is a third. 2 to the 9 minus 2 times 2. Okay. And what you'll see is this is going to be 500 over 3, which is 1,000 over 3. Okay. And that was nice because I didn't have to really deal with the lower bound at all, right? It was just 0, right? So that's cool. Okay. Now let's look at another example I want you guys to try. So the integral of excuse me, um, negative 3 to 3 of negative 5x cubed plus x, excuse me, let me just leave it as x cubed dx. Okay. So you need to check, is it symmetrical bounds? And is it even or odd? Okay. Most functions are neither even nor odd, so um, most of the time we can't use this trick. Okay. But on this one you can. Okay, so I'll leave the previous problem on the board. Go ahead and pause here and try it. All right. Hopefully you guys paused. So for this one, symmetric bounds, easy to see, right? Negative 3 to 3. That's not the difficult part or the time-consuming part. I need to check if it's even or odd. So I'll plug in negative x. So I get negative 5, negative x cubed. Okay. Now, what's happening here? Negative x cubed, that's negative x times negative x times negative x, right? Is an odd number of times. So I do have a negative. Negative 5 times negative x cubed. Okay, those negatives cancel. I get 5x cubed. Ah, that's not my original. So it's not an even function. Is it odd? Okay, so let's stop here. Not even. Is it odd? We're going to multiply both sides by a negative. Okay, just like that. All right. Is that my original? And it is. That is my original. Okay. So this is not even, excuse me. This is odd. Check. So because my function is odd, this integral is 0. Boom. Okay. Now, just so we remember, sine x is odd and cosine x is even, okay? If you look at the graphs, it's very easy to see, right? So for example, sine x looks like this, okay? So hopefully you can imagine rotating the graph 180 degrees and that you get the same graph. Then with cosine, it looks like this, right? So hopefully you guys can see it's a mirror reflection across the y-axis. That's an even function. Okay. So that will definitely help you, right? This tool here is one of those things where if you remember it and you see it, it'll help you every once in a while. Just make things go way quicker. Okay. Um, yeah, so it's really up to you if you notice. This will probably be a great true false question on an exam for you guys. Um, but yeah, all right. Thank you guys. Have a good rest of your day.